Good evening. My name is Stephen Blundell, and it is a great pleasure to welcome you to the Brebis Bleaney Memorial Lecture of 2021. This lecture is named in honour of Brebis Bleaney, 1915 to 2006. Brebis obtained his DPhil, his doctorate, in 1939 under Sir Francis Simon, who he later succeeded as Dr. Lee's professor in 1956. Brebis did war-related work on radar, developing many klystrons, and it is said that one of the most important packages to go across the Atlantic during the Second World War was a klystron that Brebis had built and designed. At the end of the Second World War, he used that knowledge of microwave technology to be one of the pioneers of a technique called electron paramagnetic resonance, or EPR. The Clarendon Laboratory in Oxford became one of the world centres for EPR research. And one of the people in Brebis Bleaney's group, Brebis Bleaney, I should say, is the person you can see on the top left of your screen, but on the top right in Bleaney's group was Michael Baker, who passed away in 2017. And Michael made many important strides in EPR, as well as pioneering a technique in which not only the electron, but the nucleus is manipulated and simultaneously addressed. Michael's work led to a number of breakthroughs, including the realization of quantum sensing in diamond, an effect that's being studied intensively to this day. Now, Michael's family have generously endowed the Bleaney Lecture according to Michael's wishes, and it's very characteristic of Michael that he didn't want the lecture named after himself, but after his mentor, Brebis Bleaney. So it's in memory of these two great physicists and colleagues, and with much affection, that we are holding this lecture today and every year. Now, this year is a great treat because we have as our Brebis Bleaney Memorial Lecturer, Andrea Cavalleri. Andrea has a degree in physics from the University of Pavia, but his career took him from Italy to Germany, Essen, to America, the University of California in San Diego, the Lawrence Berkeley National Laboratory, until in 2005 he ended up in Oxford and joined us here as a fellow of Merton College, the same college as Michael Baker. But in 2008 we lost him. He moved as a founding director of the Max Planck Institute for the Structure and Dynamics of Matter, where he has pursued his world-leading techniques on driven quantum materials that we'll hear much more about now. But like any good quantum object, he retains some overlap with Oxford, so we still have him here and contributing to the academic life in Oxford, as well as, of course, pursuing his research in Hamburg. His prizes are many. I'll just mention the Max Born Medal of the Institute of Physics, the Danny Heinemann Prize, the Isaacson Prize of the American Physical Society, and many more. He's a very distinguished physicist who's made very many important contributions to the study of quantum materials and many other systems. And so it's my great pleasure to invite Andrea to deliver the Brebis Bleaney Memorial Lecture. Over to you, Andrea.
Thank you very much, Steve. And good afternoon, everybody. I'm really very pleased and honored to be able to give this lecture. I also remember Michael Baker very well, who was at Merton still when I was there, when I'm teaching there. I joined the Clarendon in 2005, so that was before Bleaney, just before Bleaney passed away. So I never met him, but it's certainly, great pleasure and honor to give this talk. Let me ask a question to the panelists, is my screen visible now? Somebody?
No, it isn't. I think you need to share your screen.
Do I share screen?
That's perfect.
Perfect. Okay, very good. So let's see. So this talk is actually about the use of electromagnetic radiation, light, in certain frequency ranges to study the physics of materials. And I think I will try to create some connection between the work of Bleaney and leading into actually the intellectual and technical background of what what my work is. So as Steve mentioned, Bleaney had really been amongst a generation of people that have developed the early techniques to make radars portable. So there was this cavity magnetron, which was a magnetron that was able to generate strong pulses of microwave radiation, which then could be used to make radars portable. And it is true, as far as what I read, that this was maybe one of the biggest contributions to the success of the Allies in the Second World War. And of course, all this generation of people, as they left the service for during the war, they used these microwave techniques for a number of purposes. Again, Bleaney was the developer of EPR, the EPR spectrometer, and the use of microwaves to study the magnetic properties of free electrons in metals and in solids. There's of course a whole group of people that have applied these techniques also to NMR. Bleaney's names, just to give you a sense of the caliber of the person, his name is usually mentioned together with people like Purcell or Felix Bloch that all were awarded the Nobel Prize. What's important to me and for what I'm about to say now is that a lot of the work that went into the development of microwave techniques for radar techniques also led to the development of the first, what were called at the beginning, molecular oscillators or masers. And here you have a picture on the upper left side of Charlie Towns with his first maser oscillator at Columbia University, and independently in the Soviet Union, Sasha Prokhorov and Nikolai Bazov developed also masers and lasers. And this work, of course, led later on to applications, and again, applications of masers and lasers to quantum electronics. I here show the birth of quantum electronics, and I here show the picture of Art Shallow and Nico Blumberg, and were awarded later on the Nobel Prize. And what was very important in these developments that again descended from the techniques that came from these microwave work was that this led to the development of a number of methods that made use of lasers for the study of their interaction with matter. So nonlinear optics was a field that was born in the early 60s, applying masers and lasers, and made it possible to study the response, the optical response of materials to these strong light pulses. Maybe the best known effect that descends from the nonlinear interaction between light and matter is the generation of new frequencies. So you shine light at frequency omega, and if the field is strong enough, you get appreciable radiation at either the second or the third harmonic, depending on the details. But in a very interesting way, this also gave new tools to study matter. So one could now all of a sudden do spectroscopy with light that with new selection rules. One could study what are called two photon transitions that have different selection rules and allow us to do spectroscopy in different ways. Sensitivity to symmetry of materials, for example, by measuring second harmonic and higher harmonic generations together with polarimetry, and various other things, surface sensitivity. So this was a really very insightful method that has been developed over and over extensively over the decades. And I think I once counted the number of Nobel Prizes that came out of this, and even by not a particularly restrictive definition, I think there must have been something of order 15 or 16 Nobel Prizes came out of these developments. So the important introduction in what I'm about to tell you starts from the consideration that all the methods of nonlinear light-matter interaction over the past 60 years has basically been developed around visible wavelengths. So the reason for this, and so one has been, lots of interesting work has been done on frequency scales of, say, order electron volts. These are frequency scales for which electronic excitations are found in materials and molecules. And so they're in this in frequency range between 10 to the 14 and 10 to the 15 eV. And the reason why this was done was that by and large, the only available sources of intense radiation were achieved by tabletop lasers, which operated somewhat exclusively in the visible range. Of course, if I consider the spectrum of excitation of solids and what I could do with radiation in these solids, I find immediately that, of course, there's not only this frequency range of the EV scale, but if I go to longer wavelengths, I find a plethora of collective excitations in solids that are really have got to do with really the way these all materials respond to light and also their dynamics and their behavior in general. And so if I go into, for example, in the mid-infrared range, I find collective excitation such as phonons. These will be something I'll talk about today quite extensively. And if you go even to longer wavelengths, one finds a number of other modes and excitations of the solids that have got to do with the general properties of these systems. And so the purpose of this talk will be to give you a flavor of some of the new applications of high intensity mid and far infrared radiation to drive materials at these frequency scales, which have by and large only been studied in the linear regime. So by using lamps and associated detectors. And so there's really a lot what I will convince you of, that there's really a large amount of science that one can explore once I can drive these modes with strong light. So some of the advances that are enabling this science actually come from developments in lasers and nonlinear optics. It used to be very difficult to do this. Nowadays, this is one table that you find in my laboratory, but you can also find at the Clarendon, where radiation at high intensity radiation and mid-infrared and Tera-Hertz frequencies can now be generated in relatively compact arrangements. So the talk today will now focus from this idea of that I just highlighted of looking at the nonlinear response of collective mode, generally of collective modes of solids. And I will primarily discuss, or will exclusively discuss as an example, as an illustrative example, the physics of nonlinear phonons. What I mean by nonlinear phonons or nonlinear phononics is the application of a strong light pulse, which is made resonant with some specific vibration of a material. Many of the vibrations of materials carry a dipole, and therefore they can be excited with light. And nowadays, by using light pulses with electric fields that can easily exceed tens of megavolt per centimeter strengths, one can easily drive vibrations of infrared active modes to displacements that are many, many percents of the unit cell. Therefore, studying the response of the crystal lattices to this very unconventional nonlinear excitation. So there's many reasons why one might want to do this. One of my own goals, and one of the most natural goals that one could explore, is the fact that one would like to study materials near a phase transition or across phase transitions, but rather than relying on the spontaneous dynamics of a transition, one would like to use light pulses, for example, to excite a subset of the modes of the solid rather than thermally exciting many of them, and drive structural transitions very fast and by selectively driving one specific mode of the solid. And this is something, of course, that can only be done if the light field is intense enough to drive distortions that are large enough to provide a large enough distortion. This is to be contrasted with the way a phase transitions happen in nature. So this is a molecular dynamic simulation of a ferroelectric transition or a caricature of a simulated ferroelectric transition that happens whilst I reduce the temperature of a ferroelectric from above the critical temperature to below the critical temperature. This is one picture of the parameter of the system for various temperatures, and you see that from high temperatures one finds the system in a new minimum where the polarization of, say, a ferroelectric is reduced to a finite value. Again, what's important is that this transition occurs as an incoherent process, and which is difficult to control microscopically, and that you can see here. If you look, you will see at long times, once the temperature has been lowered enough, one finds these blue balls that have been offset from the center and therefore created the ferroelectric transition. What we would like to do is to use light to drive the same phenomenon or similar phenomena in, say, a fraction of a vibrational mode, therefore making it possible to drive these effects in new ways, and to, both for understanding the physics of what's going on and for applications, perhaps. So, again, this is what I'm talking about. Driving. I'm imagining a situation in which a light field comes and drives a phonon directly, a single mode of a solid to large amplitudes, and I'm trying to understand what the underlying physical set of phenomena is. So first up, before we venture into a little bit of maths, but not too much, about what how I should think about nonlinear phononics, let's first think about linear phononics. How does a single phonon, a vibrational mode of a solid, respond to a light field? Provided that the mode is odd against inversion and has a finite oscillator strength, and if the wavelength is long enough, let's say it's only at the center of the Brillouin zone of a solid, this infrared active mode will respond to radiation. And I can understand how the response is by basically writing down the potential energy of a phonon in a laser field. So this potential energy has two components. It has the potential energy of a spring, which is proportional to the square of the normal mode coordinate. So that's the coordinate of the phonon. And then it has a term that has to do with the interaction between the laser field and the charged phonon. So it's an electric field times a charge. So Z star is a tensor that tells me how much the charge of a single phonon is, times the coordinate. And from this, I can derive the equation of motion, which in this case is trivial, is that of a damped harmonic oscillator. And this is why I see certain peaks with a certain width when I look at the reflected mid-infrared light or Tera-Hertz light close to the resonance, with the phonon. So if I can now generate light fields that are strong enough, obviously this type of treatment will not be sufficient anymore. So two things are going to happen. If I now have a large electric field and therefore large displacements of a driven mode, all of a sudden two things will happen. Firstly, the normal mode that I was describing before, which I called QIR, is no longer the only mode that responds to the solid. So I have an energy that I should consider all the potential energy contributions of all the phonon modes. Plus, there's going to be an anharmonic term, which I will tell you about in a second, plus the same laser interaction term in the energy that I was discussing before. And so to zero, without knowing anything about the material, the anharmonic coupling term will include all the coupling between all different phonon modes, the third, fourth, and higher orders that will participate in determining the energy of this driven material. Okay, so for the purposes of what I'm going to tell you in the next few slides, we should simplify this problem as much as possible. So we're going to just say that we're going to make three approximations. First, we're only going to consider two modes so we're imagining a material that only has two modes, one that I'm driving and another one. I will restrict myself to the lowest order coupling, so the one that only mixes cubically, to third order 3 phonons. And I will also think that imagine the material being inversion symmetric. And therefore, this will sort of thin down all these anharmonic terms all the way down to a single term here, which is proportional to the square of the driven infrared mode, which is the one that I'm driving with a light field, times some other mode. So this is the lowest order coupling, anharmonic coupling term that I can think of if I make these 3 assumptions. Just to remind you, this is the term that gives you thermal expansion, this Q square Q coupling when one studies basics of condensed matter physics. The lowest order expansion of the anharmonic interactions in a solid are of this type, and are of the type Q square and then strain here and gives you thermal expansion. But anyways, under these assumptions, I will consider what the physics is of a material with 2 modes, with inversion symmetry, and with this type of anharmonic coupling. So let's see, I'm gonna, to show you what I can do with this, let's walk through this. I'm gonna use a light pulse, again, that drives this specific mode. And I'm gonna imagine that along the coordinate of the driven mode, the response of this specific mode is fully harmonic. At large amplitudes, this will not be the case, but let's imagine that this is the case. And therefore, the equation of motion of the directly driven phonon at the resonance, where linearly I only see response of this mode, will be that of a damped harmonic oscillator, which is something I already told you before. Now, unlike in the linear response case, where only this IR resonant mode will respond to radiation resonant with this frequency, and because of this Q square Q coupling term, the second mode, which is not resonant with the drive, will also experience a force, which is proportional to the square of the amplitude of the driven mode. So this is the first effect that I see when I have 2 coupled modes, and the first one is being driven to large amplitudes. And because the force, if the force is proportional to the square of a sinusoidal wave, whilst the directly driven mode does not have oscillates about an equilibrium position, the force that acts on the second mode will be proportional to the square of sine, which now has a direction, and therefore the mode will be displaced. Okay, so I've given you a little bit of this just to remind you that to lowest order, what will happen is that if I have 2 oscillators that are coupled with one another, sorry, somebody, anonymous attendee, wrote a question. So I'm trying to get rid of this, sorry. Basically the physics that I've been telling you about is one in which I have a directly matching 2 pendula that are not independent, but they are coupled by this Q square Q coupling that goes through this line here. And I drive one resonantly, and as long as I'm driving the first one resonantly, the second one stays displaced. So this is also, I can think of this as thermal expansion, or I can think of this as the phonon equivalent of optical rectification in nonlinear optics. So there's many equivalent effects. What's very interesting about this is that this can be thought of as a pressure, as a distortion of the material along one single mode. So this is in this plot here, I have plotted the coordinate of the driven mode as a function of time, which comes out here along this coordinate, and the second mode, which here I call QR for other reasons, and that would be uncoupled harmonically, but becomes coupled because of this anharmonic coupling. And because of this coupling, what happens is that as long as the drive is on, what will happen is that the material will be distorted along the coordinate of the second mode. So what will happen is that I will create a crystal structure that is not stable at equilibrium and that is only created as long as the first phonon is being driven by virtue of the fact that the system is, that work is being done on the system. And so one can use this method to design crystal structures in ways that they can expose new physical properties that I would not have at equilibrium. And this can be done selectively. And so this was something that at the beginning we were actually quite interested in trying to look at what modes can one drive if one studies this response of a solid. So 2 words about the selection rules. What are the rules that, which types of modes will be displaced if I'm driving a specific infrared active mode? So for various reasons, those of you that don't want to get into this should just take my word for it. If the material is centrosymmetric, what will happen is that if the driven mode is odd, the displaced mode, so this guy here, will be even against inversion. And furthermore, if in most cases, it will also be a totally symmetric mode. So what will happen is that the mode that is being displaced in this way will tend to retain the crystal structure and the symmetry that the material had before being excited. So this may look like not a particularly exciting way to drive a material. Of course, I take a material in negative times, I drive a specific mode, I do all this work to drive a distortion, except that in these conditions, I can drive distortions that preserve the structural symmetry of the material, which is not exactly what I had in mind when I was thinking about driving a phase transition into a solid. So we will have to find more sophisticated protocols to do this, but for the purposes of this introduction, let's imagine this situation. It turns out that even displacing the lattice along totally symmetric coordinates allows you to do interesting things. So this is useful every time I want to undo a distortion that I don't like. So every time I have a system that is in a low symmetry state, and I would like to raise the symmetry of the system. So we've shown in certain, for example, in certain materials, what we've shown is that in certain insulators, which were insulators because the bond angles were all irregular, let's say, or bent, one could apply this method to drive the material into situations in which the bonds were all straight, and therefore taking a material that was an insulator and making it a metal selectively with certain phonons. We could also change bond angles in other materials in which we used femtosecond X-ray free electron lasers to validate. And also sometimes melt density waves that are detrimental, for example, for superconductivity, thereby enhancing superconductivity. So in principle, even in the most boring incarnation of nonlinear phononics, where the distortions that I'm inducing are only totally symmetric, I can find situations in which this can be used to our advantage. Again, along the lines of what can be done by applying pressure to a system. Other things that one can do, again, along the same spirit of what I said, what thermal expansion is, which is the coupling between the square of an oscillatory set of modes with the strain in the material. I can exploit this type of term, which couples, again, Q square to the stress and the strain of a material to generate strain in a solid. What's very nice about this is that normally if you were to shine lasers, there's a question here. So anonymous attendee, for M. Rini et al., you said that the bond angles can be straightened by an incident laser pulse. How can this be done? So the point is that I excite a certain vibrational mode, which then I excite a vibrational mode which couples to a symmetric mode of total symmetry, a totally symmetric mode, which straightens these bonds. And there's a particular type of AG mode that maps this structure onto this structure, thereby not reducing the symmetry, but raising the symmetry. I hope this answered the question. So I'm imagining this is okay. So by the same token, I can exploit couplings in which this particular excitation couples to strain, therefore changing the volume of the material. But what I was trying to say is that normally if I shine a laser pulse onto a material, what I will only be able to do is to increase the volume of the material and therefore generate what I would call tensile strain. So strain that enhances the lattice constant. But by choice of certain protocols, I can also create compressive strains and play with strain. I will make only one example of an interesting effect. This is work done by my student Tobianova, who took the famous failed ferroelectric strontium titanate, which is also known as a quantum pyroelectric material, which never acquires ferroelectricity at any temperature, despite coming very close to it, at all thermally accessible states. We have shown that by using light and applying strain in this material, we could induce a ferroelectric state up to all the way to room temperature. This was a metastable ferroelectric state in ways which cannot be done thermally, for example. So these are all examples of a seemingly uninteresting type of phononic coupling in which one could take a system like a failed ferroelectric state in strontium titanate and thereby and with this induce ferroelectricity. So this closes the introduction to what I'm going to tell you, and I'm going to now get into slightly more sophisticated and interesting or more recent applications of this type of phonon excitations. So what I'm going to discuss now is, of course, now let's say instead of using two modes by people from nonlinear optics, you can mix all sorts of modes. And so what happens if I now consider three modes that are being mixed instead of two? So you can take, let's say that you have two lasers that now can pump both one mode and another mode. And what you will now be looking for are effects which are dominated by these terms, which instead of being Q square, Q3, Q2 in the other, would be this mode times this mode times this mode, okay? This was actually something that was proposed to us. It was raised by Paolo Radelli when he was a visitor, a sabbatical visitor with us. And the point that Paolo made very aptly was that there's two good things if you start pumping only one phonon and look at what happens to the second phonon. But if you pump two and look at what happens to a third, firstly, is that the idea that the third phonon can only be totally symmetric is no longer true. If you know enough as much group theory as Paolo knows, you'll know that if you take a B1U mode and you multiply it by a B2U mode, in certain cases, you will have a distortion along a mode that has a lower symmetry than the totally symmetric one. And most importantly, the strength with which you couple to this mode will depend on the relative phase between this phonon and this phonon. So all of a sudden, you find yourself in a situation in which the force that you apply on this other mode is directional, meaning that you can either move it to the right or to the left, depending on the relative phase of whether, this guy is moving to the right and the other one is moving. So let's see. So this is depending on the relative phase between the two, if the phase is 0 or pi, the third mode will be displaced to the right and to the left. And so this was actually comes with a proposal which we then experimentally proved to be correct, which we applied in a well-known piezomagnetic material, cobalt fluoride, which is an antiferromagnet, which when it's strained in either in the compressive direction or the tensile direction, can unbalance the crystal field environment around these two spins of the antiferromagnetic pattern and make it inequivalent, making the material a ferrimagnet, or effectively a material with a ferromagnetic moment. So what's very nice about this is that one, you can now do this in two directions with a laser pulse, and exactly as Paolo had predicted in his paper. And secondly, because these are not strain, but these are optical phonons, and these distortions happen at constant volume, I can drive distortions that are 3 orders of magnitude larger than I can drive my distortions much larger than the ones that I can drive by strain, because at some point, if I apply pressure on a material, the material will crack. And I can drive changes in the magnetic moment that are 3 orders of magnitude larger than any piezo-magnetic effect that was shown. So this was very beautiful work, which was proposed theoretically and was demonstrated by my postdoc, Ankit Disa, who has really wrote a very beautiful paper that we're all very proud of, and he's just joined the Cornell faculty on the back of this work. So we're all very pleased with this. Okay, so now so much, now you could do all sorts of things with 3 phonon mixing, but you can also have a lot of fun. You can just open a nonlinear optics book and look at what other effects. Up to now, I've only discussed with you the effect of cubic coupling. I'm sorry, there is a question. Do such higher order couplings need to be explicitly accounted for in the previous applications? Yes, absolutely. So of course I have now, so the question is, every time I look at Q1, Q2, Q3, do I also have to worry about Q square Q coupling? I imagine this is the question. I imagine, no, maybe the question, yeah. And of course this is the case, but we have chosen an application in which in the specific case of cobalt fluoride, in which the effect of the 3 phonon coupling is the only one that acts on the magnetism. And if you're asking instead, now that I read the question better, do higher order couplings need to be explicitly accounted for in the previous applications? No, because in the previous application, I was only pumping 1 phonon, and therefore I could not have a Q1, Q2, Q3 coupling to any that would be large enough in amplitude. Okay, anyway, sorry for this is a little bit difficult to give these talks, so I hope this is coming across clearly. So let's go to higher orders, quartic coupling and higher. There's also a lot of very interesting effects that one can take. Up to now I talked to you about Q square Q, Q square sigma, Q1, Q2, Q3. These are all effects that have got to do with quasi-static structural deformations and the effect that those have on the physics of the material. You can look at effects of 4th order, such as Q square, where I could achieve quantum squeezing of phonons, for example, reducing the noise on a specific phonon mode at the expense of the coupling to another one. Parametric amplification so I can almost make a phonon laser by amplifying these phonons by many orders of magnitude. And high order responses. I'll just very briefly make an example of where this QIR to the N turns out to be interesting. So very briefly, you can take a material and just pump 1 single mode. This is a material which has a very strong, in this case is a particular ferroelectric, but it's not very important, which has a very strong anharmonicity in the phonon coordinate. And I can drive this mode to very large amplitudes, okay? When I look at this now in linear response, of course there's techniques where I can follow the response of this mode with a second laser pulse. And whilst at low amplitudes, at low excitation amplitudes, only the harmonic term of this energy is important, therefore I get a perfectly harmonic response. If I look at strong fields, I can get a very anharmonic response, which manifests itself into a series of phonon harmonics. These are all overtones that all simultaneously build up the vibrational response of the material. And what my student Alex von Heugen did was to use this to reconstruct to do basically a tomographic measurement of the interatomic potential along this specific normal node coordinate. So in principle, this could be seen as a way of measuring the interatomic potential that certain atoms feel at amplitudes that are far larger than the ones that are usually achieved by doing measurements such as neutron scattering or other inelastic probes such as Raman scattering. Of course, normally, if I look at the line widths in neutron or Raman scattering, all I will know is the way the potential looks very close here to the equilibrium point. But by this large excitation and by studies, one can find ways to try to map the interatomic potential down to third, fourth, fifth expansion, and then compare this to, for example, ab initio calculations. So beyond phononics, one can apply these new methods to study other effects. I don't have only to worry about phonon-phonon couplings. I can also consider, for example, the driven electron phonon coupling. How, what is the response of electrons or of the spins in situations in which I drive this? And I will just here give you three, just as a matter of listing, three things that we've done. There's again work by my student Tobia Nova, who's the same that did the work in the ferroelectric, who took certain excited phonons in certain ways in which phonons could be driven now in circles by combining pairs of excitations that would go in quadrature with one another between two phonons that are quasi-degenerate. What he showed was that he could exploit an anharmonic term of the type Q1 cross Q dot 2. So this is something that basically has to do with the angular moment of these atoms that now are undergoing a very strange motion that they would normally not undergo. And he has used this to align and to drive spin excitations in a magnetic material. Other work that we've done has been, for example, in graphene, where by driving graphene close to a phonon resonance circularly, what my postdoc James McIver showed is that you can open a topological gap in otherwise a material which does not have any gap, and thereby showing a light-induced anomalous Hall effect in a system that does not have otherwise topological interesting structure. And he has shown that in this way you can mimic the Haldane Hamiltonian in a very elegant way. And thirdly, this is newer work where we look at the coupling between phonons and plasmons. These are only examples of things that can be done, and should lead me into a few slides on the which I really wanted to tell you, which is really the things that I'm most interested in our current work. So can Steve or Paolo, how much time should I speak for now?
I think if you went on for another 15 minutes or so, that's okay.
Okay, perfect, perfect. Okay, so let's see, summarizing what I've told you about before. Amongst the many things that one can do with strong field, Tera-Hertz, and mid-infrared optics, I have chosen the case of phonons. I have discussed the physics of driven phonons in certain situations which lead to specific distortions. I've discussed ideas of three-phonon mixing, and now I've only basically listed a few possible examples without getting into more detail. What I would like to spend the last 15 minutes on is a set of experiments which are really challenging very much our understanding. So the difference between what I told you before and what I'm about to tell you is that whilst what I told you before is reasonably well understood by considerations that we can derive from textbooks and a little bit of work, there's also a lot of interesting work that we've done, or work that is interesting to us, that we've done in superconductors, in which we have some rather striking effects, which we don't really understand very well. But I will walk you through these experiments in somewhat in a historical way, and I will tell you what we understand and what we don't understand. So the idea that we had at the beginning, which was actually maybe a little bit of a optimistic expectation from experiments, was that basically one could take a material in which one knows that certain lattice distortions are known to pair electrons and generate a superconducting state. And we thought that we should be able to find some judicious combination of phononic protocols to stimulate this type of pairing. Normally, the reason why two electrons pair is because the phonons help screen away the repulsive interaction. But we thought that maybe in some form of driven phonons, we could stimulate pairing and condensation. So let me give you a little bit of this. Of course, this idea that you could try to use light to enhance superconductivity is not new. The most striking, in my view, demonstration that dates back to the very early days of BCS superconductivity. So this is work done by Wyatt and many people afterwards, who showed that in certain microbridges, they could irradiate a BCS superconductor with microwave radiation at frequencies that are lower than the superconducting gap, thereby changing the temperature and the density of quasiparticles above the superconducting gap, and somehow fooling the material and making it think that it's at a lower temperature than it is. So this is described very nicely in this Eli-Ashberg theory that came after a few years and gave a very nice explanation of these effects. Here I'm showing critical current enhancement as a function of microwave power. And in these cases, what people have shown, and this is reasonably well understood, is that one can enhance TC in this driven state by something of order, let's say, tens or hundreds of millikelvin. There's also some work in the 90s where people irradiated with UV radiation underdoped cuprate materials and showed primarily by way of annealing, although you can't really see this if you read those papers, by way of annealing, they've achieved superconductivity as if the material was optimally doped. So they basically use these methods to improve the atomic and electronic structure of these materials. What we have done in the last few years has been to apply phononics to try to do something similar in a more rationally designed way to try to control the crystal structure. We've done work in cuprates, which I will not talk about, except to mention that when you excite YBCO with specific phonons, you can induce effects that look like transient superconductivity that I'll tell you about after, up to really very high temperatures. And this is a completely different story that I will not be discussing. But what I would like to get to is instead the physics or the experiments that we have done in which we've used resonant excitation of certain molecular vibrations in both in the doped fullerene superconductors and in the kappa, in certain charge transfer salts, in which we've used light to drive certain vibrations to try to enhance superconducting features in these materials. So the work I'm about to tell you is the work of 3 PhD students. This guy that discovered this effect is my student Matteo Mitrano, who discovered the effect, who's now joined the Harvard faculty on the back of this work. Alicia Cantaluppi, who did very beautiful experiments in the same situation under pressure, and Matthias Budden, who just graduated, who will discuss, who has shown how the lifetime can be modulated of the state. So I will summarize the work of 3 people and of a large group of excellent scientists that have collaborated with me over the years. So I will tell you now a little more about the physics of this specific material that we chose. This is potassium 3C60 superconductor. You should think about this material as an FCC lattice of C60 molecules, which have been doped, electron doped 3 times by the presence of this alkali atom. So you should think about an FCC lattice of C63- molecules. And this is a material that exhibits superconductivity at approximately 20 Kelvin. This is a measurement on materials that we grow in our lab with a molecular beam epitaxy and make thin films of these materials grown by my postdoc, Erwin Wang. And so this transition, of course, manifests itself in all the expected features of superconductivity, but also can be detected optically by doing Tera-Hertz reflection measurements. And this is, basically one can diagnose the presence of a superconducting state simply by looking at the linear reflection at Tera-Hertz frequencies of a probe light pulse. This is, of course, something that we all learn in condensed matter physics courses. When a material, which is a metal, which in this case is the C60 superconductor, which has a metallic optical features at temperature above Tc, becomes a superconductor, what one obtains is a situation in which the reflectivity, the reflection coefficient, becomes exactly 1 all the way to the superconducting gap. The real part of the optical conductivity has a delta function at 0 frequency, which I don't see here, but has a gap, which now you can see in equilibrium when I cool the material below Tc, all the way to the gap 2 delta. And also in the imaginary part of the conductivity, one sees a divergent imaginary conductivity, which reflects the presence of a pole at 0 frequency in the real part. If this was a semiconductor, I would have a gap, but I wouldn't have this divergent sigma 2. What this divergent sigma 2 tells me is that there is condensation going on at low frequencies. So, and the reason why this material becomes superconducting is the following. Let's think about an individual C60 molecule. This is the undistorted molecule. These are 3 degenerate orbitals, which are the lowest unoccupied molecular orbital, which I'm now doping 3 times, as I said, because of the presence of the potassium atoms. And now, if without anything else, one might expect a high spin state because of Hund's rule coupling, except that this molecule is unstable against a lattice, Jahn-Teller distortion, by virtue of which the material acquires a low spin state. And this is very well known from, for example, NMR measurements. And the superconducting state is actually something that has to do with fluctuations between the various ways of arranging this low spin state, these 3 electrons over the 3 orbitals mediated by vibrations of this molecule, okay? So this is basically the way we understand superconductivity in potassium doped C60. And what Matteo Mitrano suggested at the time was that maybe if we use a suitable mid-infrared pump, which can reproduce fluctuations that are the ones that mediate pairing in equilibrium, maybe we can stiffen up the superconductor and enhance Tc. So what he proposed was that I would pump, he would pump this material with mid-infrared light, and then he would probe with a second pulse in search for the opening of a gap. And lo and behold, this is what I told you about before. This is the equilibrium features that I see if I cool the material below Tc. What Matteo did was to photoexcite the material above Tc, and he showed that by taking this is at 100 Kelvin, 5 times above Tc, by exciting one specific vibration of the material, he could obtain optical properties that are really very similar by any standard that one can apply to the ones observed when cooling below Tc. So the only difference that you see here is that the gap appears to be larger than the one that you have at equilibrium. Although the sigma 2 divergence, which tells you how strong the density of Cooper pairs is at 0 frequency here, or how dense the superfluid is about the same. So this was really a striking, at least it was very exciting for me when I saw this. And what he showed was that, depending on how you define this putative light-induced superconducting state, you could convince yourself that the effect certainly was observed up to 100 Kelvin, and one would find a finite gap all the way to room temperature. So this is data that is really quite, this is the data that was reported at the time. What we've done more recently is to try to address, it's of course very nice that we are creating this superconducting-like features in the driven material, but the effect lives really for a very, very short time. And so it opens all sorts of problems, aside from the fact that it also makes it not particularly useful to have a superconducting-like state that disappears immediately when I'm done pumping the pulse. So here I'm plotting the size of the gap or the spectral weight inside here that goes from a finite number to 0 back to a finite number in about 1 picosecond. So Matthias and Thomas Gebert, what they did was to develop a new set of laser sources that would allow us to do the same experiment by stretching those, by having pulses that were now much longer. This has to do with, I won't discuss how this was done, but this was the required development of new technology. Courtesy of taxpayers, of German taxpayers' money, we were able to build a new laser that could drive the material in very long times. So what they discovered was that now, instead of driving the material with 1 picosecond pulses, we could drive it with pulses that were 300 picosecond long, and they could reproduce the same superconducting-like features, reflectivity of 1, gap in sigma 1, and divergence sigma 2, at far longer time delays than what I could observe before. So it appears that by driving the material with the same fluence longer, one acquires a state that is somewhat more rigid and actually lives, we found that it can live for about 12 nanoseconds. Okay, so this is a new discovery that is very puzzling. But it's one of the most exciting problems we're working on, and we really have no idea what is going on. And it looks like the initial intuition of driving a specific vibration to generate a long-lived, high-temperature superconducting state may not be the correct one. So things that we're doing now, of course, now that we have longer-lived superconducting-like states, we have measured resistivity using 2 probes, and we could show that at least we have with 2 terminal measurements, which require some calibration. We showed that the resistivity of this light-induced state, let's say, is compatible with 0 resistivity. It drops by, if you're careful, by 2 or 3 orders of magnitude at least, and stays low for about 10 to 30 nanoseconds, depending on how you fit the data. There's actually work that we did in collaboration with Dieter Jaksche at Clarendon and his group, who basically tried to calculate and fit our relaxation by calculating what the time would be for the nucleation of phase slips and phase fluctuations in a superheated superconductor, and using basic parameters from the well-known parameters from the superconductor, and simulating this with a time-dependent Landau-Ginzburg formalism. They were able to explain, at least in principle, why even a superconductor that is superheated by 5 or 7 times higher than TC could live for so much time. So what we're doing now, and then I'm going to close, is we're trying to develop methods to study new other features of the superconducting state. So we are trying to use magnetometry by using specific garnets that can be used to probe the magnetic field outside the material, to probe expulsion of the magnetic field in this light-induced state. So this is work that is led by Gregor Iotsu, who was actually a student in physics in Oxford and has joined me as a postdoc. Michele Buzzi, who's also quite a capable scientist in my department, and my student Giovanni De Vecchi, who are trying to demonstrate that this state also expels the magnetic field. And also other work that is going on are advanced measurements in which we're trying to measure critical currents at short time scales. So this is, again, work in progress. So how far can we take this? I suppose that what one should try to do, if I can make a 150 Kelvin superconductor for 10 nanoseconds, maybe we should try, really the dream would be to take a material at room temperature and use an excitation protocol to keep it superconducting in steady state, And so, you know, it doesn't hurt to dream. And this is really the ultimate goal that this type of research in this specific material is leading us to. So I would like to conclude by advertising this technique of nonlinear phonons and generally nonlinear Tera-Herz methods as a new tool that is added to a suite of techniques such as strain, twisting, manipulation, interfaces, microstructuring to engineer the properties of materials in some sense in a different way than what is done in equilibrium, in some cases with larger amplitudes than what would ever be possible in equilibrium, but also in transient ways, which has the advantage of being much faster, but also not infinitely long-lived. So with this, I'm happy to, I thank you again for hosting me for this lecture, and I hope I have entertained you with some new developments and have interested you with this, and I am happy to take questions if there are some. Thank you.
On behalf of other people, I will applaud. Thank you so much, Andrea, for an absolutely fascinating lecture. It is now open for questions. If you want to type a question in the Q&A, then I'll field that for Andrea. Just while questions are amassing, maybe I can just begin. One of the things with your experiments that I didn't quite understand, can you apply a magnetic field to the sample as well? Because that could be interesting in tuning states. Yes. With a field.
So I sorry, this went by a bit fast. We are trying as hard as we can. The way, okay, let me say two things. What we're trying to do is to show that if you take a material and you apply, and you can measure optically the magnetic field expelled from the material before and after photoexcitation, you should be able to see this. We've been very good at destroying superconductivity. We have not been that good yet at detecting the Meissner effect, but this has to do with if you're familiar with the difference between in-field cooling and zero-field cooling, this has to do with a complicated protocol that pumping a material many, many times reduces the effect by several orders of magnitude, because you can, you generally be observing in-field cooling, which is of course much lower than the zero-field cooling effect, although some will say that is the only real Meissner effect that one should be looking for. So of course, we're also trying to do other things in the Meissner regime, although the methodology of magnetic fields at short timescales is not quite there yet. So we're trying to improve in that department. I hope this is a satisfying answer.
Yes. I mean, what size of magnetic field can you apply in your setup? Because I was also thinking not only on the superconductivity, but your beautiful measurement where you measure the interatomic potential. It would be very nice to see how in certain non-superconducting materials, those that show magnetostriction or interesting magnetostructural coupling, whether you could measure those kinds of curves in high field and see if
in principle, okay, two answers. Answer number one, in the specific case of the superconductor, we are trying to apply a field in the Meissner regime, which in these materials is a millitesla. So as small as we can get away with. Of course, in the other case, we could do these experiments in a large magnetic field. At the moment, we have a 5 Tesla magnet that we bought at the supermarket for magnets. But of course, if you could synchronize a pulsed magnetic field with a laser, you could consider doing these experiments. Of course, there's issues of repetition. We talked about this with Paul Goddard 10 years ago when we were talking about FELs. Of course, there's duty cycle considerations. These experiments are done by doing the experiment 1,000 times a second and acquiring for a long time. If you can pulse your magnetic field once a minute, you better have an experiment that has a high yield. So practical considerations notwithstanding, at least, let's say, if you can buy a large DC field, lots of things can be done in this regime. Yeah.
Thank you. A question from one of the audience, Paul Coe, has said, is it possible that the longer driving infrared or Tera-Herz pulse makes several round trips inside the sample? Perhaps the temporary refractive index contrast of the sample compared to the surrounding air makes for a high Q resonator on short timescales, allowing several round trips and therefore several nanosecond lifetime of the effect?
Okay, so this is a very interesting question, the answer to which is no, because the material is a metal and I am exciting at the surface. But it's a very interesting question for at least two reasons. Firstly, is that I do think that in the when the material is being driven by long pulses, what I'm really doing is enhance the correlation length or the coherence length, sorry, the correlation length of the superconducting state, perhaps to sizes that are far larger than that of a vortex, and thereby making the state metastable rather than just disappearing immediately. The second reason why what Paul says is very interesting is that there's all sorts of proposals in which one could embed these materials in a cavity, in an optical cavity, and modify and enhance and make more, enhance the interactions between the laser field and the material in the context of a high Q resonator. Perhaps put yourself in situations in which the thermal management, you don't need to pump quite so hard, and therefore you could just, avoid, you could induce this effect better with stronger fields. And there's another 10 reasons why this is a very interesting question, although in the specific case here, it doesn't really apply.
Thank you. Another question, have you done time-resolved pump probe studies of the pump-induced superconductivity?
Yes. So
I think you have, haven't you?
I have. We've also worked with the free electron lasers to study the structural distortions. We've applied a suite of techniques. I mean, when you say pump probe, of course, the pump is being defined. The probe can be all sorts of things. There's many nice things that one could try to do, such as photo emission and various other things. At the moment, we've only applied optical and terahertz responses, sort of probe responses, which I showed, and also some X-ray free electron laser work, which is giving some information, but not everything.
Right, thank you. Somebody else has asked, how exactly does the nonlinear phononics apply strain to a material? I think somebody just asking you to tease that point out a bit more.
So, I mean, let me go back to the beginning. This is, I mean, I could take you to Ashcroft Mermin whenever, Steve, you know what page it is probably, when he describes thermal expansion. Let's see. Where is this? Okay, so remember, we restricted ourselves in this anharmonic coupling term to coupling terms of the type QIR squared, which is the mode I'm driving, Q2. Now, this Q2 mode can be any mode that is allowed by symmetry. It could be an optical phonon, which preserves volume, which is the more interesting one, or at least the one. But it can also be a strain, say a zone center acoustic phonon that changes the volume. That changes the volume of the material. So this is really, if you look at it, you should look at coupling terms between Q square and the stress, which is really a pressure, an internal pressure, which then gives rise to a motion. But once again, when you consider when you think about increasing the temperature of a material and understanding why the material compresses or expands, it's this coupling. You have all the thermally excited phonons, which are rectified because they come in square, and then couple to an acoustic phonon, which then increases the volume. So it's exactly the same thing, except that this is done non-thermally by selective excitation of QIR, except that thermally. I hope this is clear enough.
That's great. And maybe there's one more question, and we'll probably make this the final one, and then we'll come to a close. But the final question is, what about strong nonlinear magnetic driving that would somehow enable the driving of a magnetic transition as well as a phononic structural one?
Yes, so this is a very interesting question. One would have to envisage a short pulse I imagine that the question is about a short pulse. The biggest problem that you have when you have a short pulse of a magnetic field is that when you have B, if you have a strong B, but you also have a strong dB dt, because the magnetic field changes in time very rapidly, you end up with an electric field that is far larger. So the problem of making a short, if you want strong fields, strong magnetic fields, you better make them in long pulses, because otherwise you're going to be stuck with a very strong electric field, which is going to dominate the whole the whole response. So a lot of people talk about strong magnetic fields in terahertz pulses for the reason of what that I mentioned above. I'm not a big believer in their applicability.
Wonderful. Well, Andrea, thank you so much indeed for answering all those questions, and even more so for giving us such a fascinating insight into this extremely interesting technique that you have pioneered over the last few years and has produced so many interesting and fascinating results. So we wish you success with the current program, the developments you were telling us at the end. And thank you again so much for giving the 2021 Brebis Bleaney Memorial Lecture. So thank you very much to everybody else for...
I'll see you all as soon as they open the border.
Absolutely. Yeah. On another occasion, we would be inviting you all for a drink afterwards. Unfortunately, that's not possible. You'll have to go and obtain your own drink. But okay. Thank you again, Andrea, and thank you very much to the audience.
Bye-bye, everybody.
Bye-bye.